Right, what makes section 6.1 so important is the application problem. So a lot of things that you come across in the real world can be modeled by an exponential growth or decay model. For exponential growth, we're going to have this general formula of a of t equals a, then in parentheses 1 plus r raised to the t power. Decay, same setup, instead of a plus, it's going to be a minus. So you remember that for decay, it's going to be 1 minus, and then for growth inside the parentheses, we're getting bigger, be 1 plus. In these models, the lowercase a is going to be our initial value. R is the rate of growth or decay. You make sure that that is in a decimal. Okay, so a lot of times they give it to you as a percent. We need to make sure it's in a decimal. And then t is going to be the time that it's going over. Sometimes they throw x up there, but realize that our exponent up top, outside the parentheses, represents our time. So putting this into practice, for example 3, I have a population of a large city, was about 4.6 million in the year 2010, and it grew at a rate of 1.3% for the next 40 years. First thing I do is pull out like the key information. So this 4.6 million is our initial value, so that's going to be our lowercase a. We started in 2010, so that's kind of a big deal. Some problems that makes more, it's more important than others. And then it grew at a rate of 1.3%, so that's our R. But like I told you up here, the rate has to be in a decimal. So to get 1.3% to be a decimal, I'm going to divide by 100. It's going to be 0.013. So for A, they want us to write an exponential model for the population of the city. Since we were growing, it's going to be a growth model. So we're going to have A of t equals my initial amount. I'm just going to put 4.6 here instead of writing out a million. And then we'll just know when we find our answer, we have to attach a million to the end. So 4.6 was my initial amount. In parentheses, I have 1 plus 0.013, and we are raising that to the t power. Okay, so that's my model right there. You also could have simplified inside the parentheses to give us 4.6, 1.013 to the t power. A common mistake that some make is they go ahead and try to multiply these. You cannot multiply them because you have an exponent outside the parenthesis. Okay, so you can't multiply those at all. You just have to leave them alone. For B, they say if the population continues to grow at the same rate, what will the population be in 2040? So if I'm at 2010 and I'm counting up to 2040, they're asking me for 30 years later. Okay, so we go ahead, plug in 30 for t. So it gives me 4.6 times 1.013 to the 30 power. Okay, that's all calculated from there. So on our calculator, we go ahead and type in, what are we doing, 4.6 parentheses 1.013, and we are going to the 30 power. So it's going to give me about 6.78 as my answer. Remember, it's not 6.78 people. It's going to be 6.78 million people. Okay, so that would be for an exponential growth model. Remember, if it's decay, it would be 1 minus. All right. Last example we have in 6.1 is example 4. So you got a car. It's purchased for $24,000. They give you the function right there. They say it can be used to model the value in thousands of dollars X years after the purchase. First thing you want to know is it growth or decay. You always focus inside the parentheses. So my parentheses is 0.8 to the x power. If it is less than 1 on the inside, okay, so any decimal less than 1 is going to be decay. So this problem right here is a decay. Reason being, our 0.8 is less than 1. Okay, so you're always looking, what is raised to the exponent? In this case, since it's less than 1, it's going to be decay. For B, they want to know what is the rate. So I know for a decay problem, it's 1 minus r. So we have 1 minus r in this case equals 0.8. So they're asking us to solve for r. However you do it, you're going to get r to equal 0.2 or 20%. So then lastly, they want you to graph it on your calculator and figure out when will the value of the car be $5,000. So there's two graphs we're actually going to do. It's kind of a system. You're going to have y equals 24, and then we have 0.8 to the x power. And then I want to know when it's going to be $5,000, so y equals 5. Remember, in the problem, they said that our money is represented in thousands of dollars. So I'm just going to let y equal 5. So from here, on the graphing calculator, you can go ahead and graph it. Remember, on your phones, the app that you could use is Calculate 84. So that's the app on the phones. Or you could find another resource online to graph them. But you need to graph both these lines. So I'm going to have 24 parentheses 0.8 to the x. And then the other one I'm graphing is y equals 5. So I go ahead and graph both lines. And let's see if they even show up. Yeah, they both show up. So what we are looking for here is the intersection point. So I want to know, okay, what point do they cross? To do that, I'm going to go second, calc, and then go down to intersect. So they asked me first curve. I'm going to try to move my cursor until they're like lined up. So I'm going to keep hitting the right. Okay, there's a cursor there. Boom, boom. And it says they intersect roughly at 7.029. Okay, so that's going to give me about 7.03 years. And on the intersection, you are looking for the x value. So on my calculator at the bottom, it tells me they intersect 7.03. So that's it for section 6.1.